Hello everyone, welcome back to my channel. My name is Cha Cha. Today I'm going to be going over Newtonian physics, which I think according to the Kaplan books comprises around 25% of all physics content that you'll see on the MCAT, which is quite a bit. Isaac Newton is one of the founders of physics, so it makes sense that this would be a big portion because all of the later physics concepts that you'll see have some inkling of basis on Newtonian physics, especially what we're going to talk about first, which is the different types of potential energy. So you have kinetic energy, abbreviated KE, and gravitational. So first I'm going to talk about kinetic energy, which in classical Newtonian physics is 1/2 mv squared. M for mass, v for velocity. And then we have our elastic potential, which is, as you could see, that's a pretty similar to kinetic energy, right? Since instead of having M, you have K, which is for a string constant, and then instead of having V, you have X. Which I guess the absolute value bars that I added aren't really necessary because you're squaring something, and if you square something, if it's negative, it's going to be positive. And X is the distance from equilibrium. And what do I mean by that? So imagine you have a string and then you're pulling it, right? If you have like, I don't know, like a slinky or something like that too, it's the same thing. If you're like pulling it from equilibrium, you could go in either direction. You could go positive or a negative direction, let's just say. Since it's going to rebound. And then X is how willing is that string, sorry, K, I don't know why I said X. K is how willing is that string to be pulled. That's kind of how I like to think about it. And X is that distance from equilibrium. So if you have something, let's say like you have a metal string, like that's pretty hard to pull, right? Metal is like pretty infallible. It's like it's very stiff. Whereas if you have something made of like straw or something easy like that, it's pretty easy to get pulled. So it's a lot less energy is required to move that string. Also, an assumption that I like to think about for spring constants and just strings in general is that your string is weightless, which is something that, at least for our purposes, if you go in higher up physics classes, that is not the case, but I'm not touching that. So, yeah, that's just something that you have to keep in mind for MCAT. Um, Yeah, and then I want to go over gravitational potential energy, which is the other basis that you'll see. So mgh. So M for mass, G is for gravitational constant for Earth. It's constant for Earth. You could see, like, for example, let's say you're talking about Mars. This will not be true for Mars, since Mars has a different gravitational constant because it's a different planet. And on Earth, it's 9.8 meters per second squared. I don't know why I forgot what's word there. Or if for the purposes of the MCAT, you could round it to 10 meters per second squared. Then H is height, so it's a height similar to the string constant. It's how far above zero or the Earth you are. So let's have like this box, it's like 20 kilograms. Oh my gosh. This box is 20 kilograms and it's 10 feet above, or 10 meters. Let's do meters, not feet, because everything has to cancel. So it'd be 20 times 10 times 10. There you go. That would be what your gravitational potential energy will be. Woohoo. Um, yeah, and then this kind of all comes together again in fluids too, for Bernoulli's equation. So basically, Bernoulli's equation is just kind of just rehashing what we've learned. So it's P1 for pressure one plus 1/2. P or rho, or not P, but like rho for density. I kind of just call it P in my head. But it's not a P for pressure, B squared. Instead of having mass here, it's density. So not mass, but density. So this is KE, which I'll write up here. And then I'll write for gravitational as MGH. And same thing here. You have rho instead of mass. So This is essentially just adding the two kinetic energy and gravitational potential energy together in Bernoulli's equation. So there's a lot of stuff that builds upon each other. If you can memorize these two equations, then you'll have Bernoulli's equation and a spring constant pretty much set. And here, I'm going to talk a little bit more about the basis for Bernoulli's equation as well, just because I'm talking about it right now, so might as well. The Venturi effect is when fluid speeds up and the pressure drops. Why is this an inverse relationship? So if you think about it, right, like logically, the slower something is moving, the more opportunities it has to hit a surface, which will increase your pressure. So if you have something that has like a large area, right? Then that means that its velocity is very slow. I mean, sorry, it's like the particles aren't moving very fast. So that means that there's more chances for the particles to hit against the walls up here. So that green is the walls of this pipe, which increases the pressure. Whereas if you have a smaller area, right, it's kind of like if you think about it, right? Like if you're squeezing, like accidentally, like if you have like a water bottle, like one of those like Costco brand or Kirkland brand like water bottles, you step on it, right? Then it's going to increase, you're increasing the pressure. Sorry, not you're increasing pressure. You're making the velocity go faster. And if you're doing that, because that's a smaller area, your pressure is going to decrease because there is less chance of those particles from hitting the wall. Um, and this is something that I just want to point out for Bernoulli's equation. And it wasn't, when I took physics too, it wasn't necessarily pointed out to me by my teacher. And I got really confused because I always thought that pressure was equal to force over area, which is true, but this is for static fluids and materials. So I was always really confused why if you were to decrease area, the pressure would sorry, the pressure decreases instead of increase because it's in the denominator, right? Area is in the denominator. So I thought if you were to decrease the area, then you're going to increase the pressure if you have the same force. But that's for static fluids and materials, so stuff that is not moving through a pipe. Whereas for dynamic fluids and material, you have A1 V1 equals A2 V2, which is what is going into Bernoulli's equation. That's kind of the basis. Also, I kind of want to talk a little bit more about laminar flow and turbulent flow, which is kind of important for fluids in general and Bernoulli's equation. This is kind of getting a little bit deviating from Newtonian physics, but I think that this is just important because we're already talking about Bernoulli's equation. So laminar flow, it is predictable. There is a mathematical equation for it. So it's pi, r as in radius, um, cubed, and then you have 8 n L, which is the length of your pipe. And then that's not really an important equation for MCAT. I have not memorized it and all the variables associated with it. And then you have turbulent flow, which is very chaotic, but the closer to the edges of the pipe are, the more similar to laminar flow, the more predictable it is. Um, Yeah, and this is just kind of like chaotic. There is no mathematical equation, or at least none that you need to know for MCAT. It's also really important to consider conversions, because if you can remember conversions, and a lot of the times this stuff, you'll be given an equation on the MCAT, and you can kind of deduce what's the mathematical, like what you need to do. Like if everything cancels out, then you're good. If everything doesn't cancel out, then you kind of need to rethink how you're ordering or manipulating the different numbers or different variables that you're given. So some conversions that are really important for gases is 760 millimeters of mercury is equal to 760 torrs, 1 atm, and which is equal to 1 to the 10th Pascal. And Pascal is really important for force conversions because 1 Pascal is equal to 1 Newton per meter square. I don't know why I have the angles here. I'm gonna go more into angles when we talk about friction and normal force. Woohoo! So, in order to understand friction, you first need to understand normal force. So, what the heck is normal force? So, we have our weight force, which is kind of equivalent to it's equal to mg, right? So, instead of having like h, right, since this is literally going to be on the earth, um, so it would be kind of counterintuitive to have your height because then your whole gravitational potential energy would be zero. We're going to have weight is equal to mg. I don't know why I have weight. Then the normal force points upwards. Well, I'll get more into Newton's three laws that he has as well, but this is an example of force pairs, which is Newton's third law. So like for something to be at equilibrium, it needs to have a force that's equal in magnitude, but it's in the opposite direction of it, so that it's not moving or doing anything crazy like that. And normal force, when something is on the earth or just any object in general, that is the opposite force of the weight force. So at equilibrium, force 1 is equal to force 2. So force of normal force is equal to force of the weight, or weight force. And then in general equilibrium, you'll have the sum of your y variables for force is equal to 0, and the sum of your f of x is equal to 0. Important. So, okay, this is kind of what we're going to get more into here. So, normal force. This is where you have, remember, you have friction here. Oh, wait, hold on. We didn't really talk about friction yet. Sorry. Let me talk about friction, then I'll go into that. Sorry. Static friction is typically higher than, or it has like a constant that is typically higher than kinetic friction. Logically, it is easier to push a box that is already moving than when it is still. So what do I mean by this? You have your static friction is less than or equal to the normal force. And then you have U, F, N. So U of S. So it's going to be less, right? It's going to peak and then it's going to start moving again. So when you have kinetic friction, right? It's a constant. It's still reliant on the normal force. Both of these are still reliant on the normal force. And then you have your constant for K for kinetic friction for the normal force multiplied by the normal force. Which is the same here. You have the constant for static friction for the normal force. So I kind of have this fun little diagram here. So over here, this would all be considered static. And then kinetic friction is over here. So the max for static friction is always going to be higher than the constant for kinetic friction. Static friction, it is up to a certain point until that object starts moving. So it can be anywhere between 0 and that point where it starts moving, the object starts moving. And then kinetic friction is always going to be a flat constant. So it's never going to have any variance, where static friction, the constant can, depending on what time point you are looking at. Okay. So now I have kind of a more complex thing. So you'll often see this in your physics classes where you'll have something that is on an angle. So this is kind of what I come back to for the sum of the forces of y axis and the sum of the forces for the x-axis. So the friction is what's going to counteract the value of the normal force, the x value for the normal force. And then weight will be the y value. Which makes sense since you have cosine theta. Cosine theta, cosine is typically something that is assigned to the x-axis. That's just something to keep in mind of how you're remembering it. So the normal is equal to mg cosine theta. So if you have a weight force, and I'll show you how I derive this as well. So you have a weight force, you're going from the center of your object, your little box here, and go straight down, right? So if something goes straight down, then it's going to form a 90-degree angle. Whereas your normal force is always perpendicular to the object that is on your incline, or yeah. So It's always at that 90-degree angle. Perpendicular is just kind of a fancy way of saying 90-degree angle. So we have this theta here. This is like the theta is equivalent to the angle of the incline. And as I said earlier, weight force is straight down, so that's going to be a 90-degree angle. So this angle, because triangles are 180 degrees, will be 90 minus theta. And then because this also, the two variables here using classic geometry have to be equivalent to 180 degrees, so equivalent to a flat line. This has to be theta, this angle here, because this is 90 degrees and this will be 90 minus theta. So using math to have this imaginary line for the normal force, because the normal force is just maybe perpendicular here onto the object itself, but it also goes into the plane just because it's not necessarily pointing upwards. You can still find the value of the normal force using trigonometric functions such as this. So then you have your theta, which will be, because it's not, you're using your adjacents line, it'll be cosine. So it's mg cosine theta, because mg, you're still using the weight force, right? That's kind of like your basis of everything is the weight force, because remember normal force is equivalent to the it's a force pair. It can be a force pair. And then you have cosine theta. And you're using cosine because it's the adjacent to said angle. Not sine would be if it were opposites, which would be here. That's not the case. And then that's how you get your friction. So it is the x value of the normal force. So mg cosine theta. And that is the proof behind it. And then you have SOHCAHTOA, which is kind of what I was talking about. So you have sine opposite, which is over here, over your hypotenuse, which would be, for example, in this case, it'd be the normal force. Imaginary normal force that goes into the angle. Then you have cosine. Cosine is your adjacent angle, which is this. And then you have your over the hypotenuse. Then you have your tangent, which is opposite over adjacent. Yeah, that is kind of how you do it. And then friction, yeah, also kind of more or less, again, like if you have it on a flat surface, it's more or less reiterating. So if you have this person that's pushing this heavy object, you have the force of the person pushing, which will go to the right. And then you have your normal force, which is in green, green pointing upwards, whereas your weight is pointing downwards. And imagine if this is a stationary object, then the friction is equivalent to the force of the person pushing. So the friction will always oppose the force of the person pushing. So it's going to be pointed to the left. And remember, if this is stationary or static, then it will be US of the normal force, or if it's moving, then it's the mu K of Fn, so the normal force, which I have here. But yeah. Then I have torque. Torque is pretty, in my opinion, one of the more complicated physics concepts. So what the heck is it? So torque is kind of the effort needed to turn stuff around an axis. F is the force applied. R is here, and then I'll here. So I have the torque is RF sine theta. So F is the force applied. R is the distance from the center of axis of rotation, are also known as the moment arm, which you will often see. And theta is the angle between the force and the lever arm. So remember, sine of 90 is equal to 1. So the moment arm is bigger when theta is closest to, or sorry, not moment. So torque is biggest when theta is closest to 90 degrees, and sine of 360 or 0 is equal to 0. So that's when there will be the least amount of torque. So everything on a right angle, that's when essentially, like when it's like straight up. So like if you're pushing straight, that's the best. That's how you'll get the most torque. Another convention, which is kind of confusing, is if you're going counterclockwise. So if you're going from 12 to 11 o'clock, right? Then that will be positive torque. Where if you're going clockwise, so from 12 to 1, 1 to 2, that will be negative torque. As I was saying, RF sine theta, that is what torque is. So if you apply the same force, here I have, let's just imagine that you're trying to push something along an axis, right? You're pushing, 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 right? I don't know. If you're pushing A, B, and C at different places, if you apply the same force to A and C, A will have less torque as the moment arm R is much smaller. Whereas B will have intermediate because you're still applying the same amount of force, but their torque will be smaller because your moment arm is an intermediate length between A, B, and C, if that makes sense. So moment arm is important. And it's much easier to move stuff the further away you are, which is why C is the best, which makes sense, right? Like if you're practically thinking about it, it's much harder to like break a pencil if you're closer to the eraser than if you're like kind of further away from it. If that makes sense. Mhm. Okay. Uh, and then I have similar to something that is on an angle. So then I kind of added a fourth variable. So L, oh, I don't know, I have. Obviously. Okay. So L is the distance just like flat between the center of axis and where the force is applied. So I'll kind of let the picture more or less speak for yourself. So R is a perpendicular to where the force is applied, meaning it is at a 90-degree angle. So this is why forces, remember, similar to when we're talking about friction with the normal force, kind of going as your imaginary normal force. It's like it supersedes all boundaries. It's gonna keep going. So I have this imaginary moment arm with the dots, and then I have the force as well, superseding past this boundary since this is where the force wants to go. Like this is its path it wants to go. So I have an angle. So a vertical angle. So theta is the same between here. This is like simple geometry, right? They're on opposing sides. So theta will be the same. Then I have an angle here. Then because you're trying to find the moment arm will be R. R equals L. So that length, right? Because the length here will be the same on each side because it doesn't make a difference whether it's on the forward facing side where that force is, or if it's on the opposing side or the back side. It's going to be the same distance because it's just flat. It's on a 0-degree angle. So L sine theta is what your moment arm will be, if that makes sense. And then you could do the regular stuff, so that's like kind of what your R will be. So plugging it in, you have your force, L sine theta, that's your torque. Booyah. Okay. Now I kind of want to go over Newton's three laws. So an object in motion will stay in motion, and an object at rest will stay at rest. So this is assuming that you don't have any outside forces. So if you have a frictionless surface, your velocity will be the same. Velocity time acceleration will be the same. It'll be 0. Whereas if you have a surface with friction, you have external force acting upon it. So friction is said external force. So your velocity will be decreasing until the point where it gets to 0, where your acceleration will be constant at negative, like for in this case, it'll be -20. Here I have the math sort of to back it up. Remember, rise over run. So y2 minus y1, run is x2 minus x1. So in this case, right, I have 0 minus 10, 0, 10, and then 10, 0. So that's -20. This is how you get acceleration. Remember, since acceleration is just delta v over delta t, velocity is delta x over delta t. And then the second law is force equals to mass over mass times acceleration. This is especially important for electrostatics as well, in my opinion, or electromagnetism, not statics. Whereas 3 is force pairs. This is kind of what I was talking about for weight in the normal force. For objects at equilibrium is they cancel out. So every reaction has an equal and opposite reaction. So I have the sum of y of the y-axis and the sum of the x-axis are equal to 0 at equilibrium. And this is kind of where mechanical advantage, or MA, this is where that also comes into play. So if I have two lines or two string lines, so or two chords, let's say. So T1 and T2, since this will have tension in it because it's hanging from the ceiling, so upside down. And I have this equilibrium portion. So where the forces are equivalent to each other. So I have my weight force is equal to 200 newtons. But because remember it's at equilibrium, so the forces up must be equivalent to the forces down because that is the sum of y, or those y-axes, right? Since this is y-axes, has to be equivalent to 0, whereas the x-axis, but in this case, there is no really x force acting upon it, that also has to be equal to 0. So assume that these two chords are equivalent in all nature. They're made of the same material, yada, 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 same length. So T1 plus T2 is equal to 200 newtons, which is what that weight force is. So you could just divide 200 divided by 2, and that is how much the tension force of each chord is. So it's 100 newtons each. Because there's two of them, you have to divide by 2. And mechanical advantage, it kind of takes advantage of those. So, for pulley systems that you need to be 2 times the distance in order to have less force required to lift it up. So in this case, it would have to be times 2. So if you have a load over your mechanical advantage, so mechanical advantage is how much like string or cord is holding up this box here, for example. And if you're like pulling it up, yeah, I'm just gonna erase this. If you're pulling up this box, this is you. That 200 Newton box is just more or less saying like how, like the force of the person pulling up that they need to use. So 100 newtons, because these two tension forces, they kind of divide the force amongst each other, right? It's more or less like if you have a group project, it takes less effort in order to contribute to or complete the project than if you were just doing it by yourself. Or at least if you have competent classmates. If not, then it can be take a little longer. But that's neither here or there for this. So your load is that total like weight or like the total energy expanded in order to lift that box up, or whatever you want to do with the box, like what you need. I guess like the opposing force is more or less what you can call it. Whereas a mechanical advantage is kind of like the shortcuts you're using. So how many people, how many chords that you're using in order to pull the opposing force up. So in this case, because you have two chords, it's the mechanical advantage is 2. Because the weight force is 200 newtons, it'll be 200. So your effort is 100 newtons. But yeah, so remember if you have 100 newtons, that means the distance in order to pull the pulley system up is 2 times the distance to lift the box up. If that makes sense. And interconversions. So this is also really important for Newtonian physics and physics in general. Like I was saying, if you can have your units cancel, then you're probably able to solve the equation, even if you don't really know where to begin. So you have newtons equals to kilograms times meters over second squared. So this is force equals ma. So how much to accelerate 1 kilogram by 1 meter per second squared? Whereas joules is how much force and to move an object 1 meter. So this is kilograms times meter squared over second squared. Whereas watt is joules per second. So this is kind of work. So how much energy joules is used in 1 second? So it's kilograms times meter squared per second cubed. And that is kind of all I wanted to talk about for Newtonian physics. Sorry if I rambled a little bit or if stuff was a little incoherent, but physics has always been one of my least favorite subjects. So hopefully that made sense. If not, please let me know in the comments, or if I made any errors, please also let me know. Once again, my name is Cha Cha.